I have been a distribute. Yep. I've been a distributed engineer for some time, and today we'll be presenting a paper on resource management in Aurora Serverless. So, as you already know, like Amazon, Aurora is a database service provided by Amazon, and which is a relational database service for OLTP workloads, and this is built on a disaggregated storage. They have MySQL and Postgres compatible versions. And for data storage, 6 copies of all customers' data is stored and spread across three Azure uh, ECs actually. And whenever a data is written to primary DB instance, this gets synchronously replicated to all the 6 storage nodes actually. So on the storage side, they use something called as storage cluster volume, which is generally like 128 or 64 TBs, depending upon the DB engine version which we are using. And for compute layer, we basically Aurora Serverless procures host comprising of 256 ECU use. I will come to what does ECU mean, which basically is Aurora computational unit actually. So Aurora Serverless is on-demand auto scaling configuration for Amazon Aurora DBs, where the customers can scale up, scale down. Basically, it's like vertical scaling up their resources. They don't support the scale out functionality yet. Uh, and Basically, like you can increase or decrease the different parameters which are there. And ACU basically stands for Aurora Capacity Unit, which is a combination of 2 GB of memory and corresponding CPU networking and block device IO throughput. And customers are charged in terms of ACU hours accounted at a 1 second granularity. Uh, the customer can define their min capacity and max capacity. And this basically allows the min capacity basically allows each DB writer or reader to hold a working set of the application in the buffer pool. So that way, like the content of buffer pool aren't discarded even during idle periods. And right now, the min value that they can set is 0.5 ACU and not 0. And that is basically like 0.5 ACUs to use, it will use minimal computational resources available, and it should be ready to accept connection immediately. And after that, like you, based on the usage, it can scale up after that, about which this talk is about. Currently, they have implemented like V1 version and V2 version. We will go over like what are the differences between these two versions for Aurora Serverless. I'm going slightly in depth here. The key ideas that we will be talking about, and these are some of the key ideas which they have implemented over. So one is like they talk about resource oversubscription, where the host can oversubscribe on CPU, memory, and a couple of other parameters. They have a reactive control, uh, which they take based on the recent measurements which they take. They have a distributed and hierarchical decision making paradigm, and they have made some of the key innovations in DB engine OS and hypervised for efficiency purposes. And they are using token bucket rate regulation mechanism. We will go over each of the topics in the upcoming slides actually. So just before we talk, like I will just give a brief history, like how AC V1 was implemented. And AC implemented this V1 version was implemented as a multi-tenant proxy of frontend, uh, which consumers can connect, and basically this proxy can help identify the target database. And the scale-up approach requires finding quiet points when the session transfer would take place, and it won't disrupt the customer performance. So there were a couple of issues with this one. So first of all, finding a quiet point become very tricky, like when the DB or database is constantly in use. Not all type of session states like temporary tables were transferable to a different backend. Another thing is like scaling is not because scaling itself like is such a costly operation. It was not possible to do in large. It was possible only to do in large increment. So basically, we can do up or down by a factor of 2. So there were a couple of, even though it was a very good step in terms of like providing the scaling up factor, but because of these constraints, like these were some of the constraints that it has. So AC, I think Azure Aurora Serverless V2 came, where we have in place scaling, which can happen while the SQL statements are running and transactions are open. It can scale up and down much more faster. And the minimal set of units which it can scale up or down is 0.5 ACUs. They are currently using two major mechanisms. One is the memory and CPU hot, basically like reserving memory and CPU units. And the second thing is they can do live migrations of instances across hosts. So these were the two key points that we will be discussing going forward. And to achieve these two, they also introduced a new VM type, which offered a memory size scalability. So in the VM type, each process, you can define the memory units in terms of different parameters, like CPU memory and a couple of other parameters. So the VM has the capability that you can provide across different hosts. So this is a very high level overview of how does Aurora Serverless work. So as you can see, like I think the two major components that we have is one is the inter-host management, which takes care about the host management across a fleet of hosts which is there. And one is the intra-host management, which take care of the management inside one of the each host which is there. Inter-host management takes care of these three functionality, like it takes care of fleet sizing, what should be the size of my fleet. It take care of live migration, so migrating one instance from one host to another where some space is available in terms of resources. And it does some kind of recommendations on HIT, which will come in which basically like it's a host recommendation for the resources for the instance I at particular time t. So we will come to this how it's being computed and all in a later stage. And it basically like this inter-host management talks to host service, which it can use to procure and release some of the host as and when required. And I think for intra-host management, this is running inside each host. I take care of a couple of responsibilities like it takes care of resource usage gathering. It collects the resources from different instances which are running there. It does the in-place scaling based on how much is the usage based on the current running queries and all and current usage. And it does a boundary management. And as you can see, like here in the diagram, there is an in transit instance also happening. So basically like this particular instance is getting migrated to another one based on the usage. And the fleet manager is also collecting the resource usage statistics from each of the host here. And it's providing the HT recommendations to it. And all this for state management or basically for storing all these different data points they are using in memory state. They haven't described anything more about what kind of in-memory state they are using in this paper. I think they have everywhere they have just mentioned like in-memory state is being used. So for fleet management, like the fleet wide decisions, fleet manager is being used, whose major decision is like it figures out what should be the fleet size at a much coarse time scale. Another thing is like we need to determine like when to do the live migration. So for that one, we need to figure out like how do we determine a host is a hot or not. So based on like critical level of utilization for CPU, allocated RAM, total network bandwidth, and these parameters, we determine whether host is hot or not. And whenever we are doing any live migration, we need to make sure of two things actually. How can we make sure like there is spare capacity on the host and the host to be migrated? So how do you figure out like which host or which instance to be migrated to another host? So fleet manager controls the mapping of instances to host, and this determines the distribution of spare capacity on the host. So take care of this. Another thing is like how can we ensure that growth in the resources needs does not outpace the live migration based remedial actions? Because when we do live migration, it's not an instantaneous thing which happens. There might be certain remedial actions that we need to take as a part of this. So there are a couple of decisions that are taken up, which we'll go over, which where we can which we figure out what's the heat management and how are the host level mechanisms we can use. And for hosts which are undergoing live migration, fleet management can also impose short-term limits on the max AEC use for its instances also. And these limits are lifted as soon as the heat has been remediated. When I say heat has been remediated, as in either the live migration has been completed or maybe whatever heavy workload which was running has already completed. So when the heat is or the resource usage is not that high, we can off limit these assets also. Just before going into depth here, I think let's try to figure out this two phases actually. One is the normal growth phase and one is during live migration. So these are some of the nomenclature which is used in the paper. So we have CI min and CI max, which is like what is the customer min bound and customer max bound provided for their usage. So that's one part. HIT is the what's the maximum which we can use. So during the normal growth phase, the HIT is equal to CI max, and basically like and UI and the current usage is currently at UIT, which is the utilization at for instance I1 at T1 time actually. And this we another parameter which is decided is something called as RIT1, which is how much is the reserved one for this one at current instance. So for in-place scaling, like from UIT to RI, this is available for instantaneous growth. So if my usage is growing fast, like this is available to me as just right now. And this can be this particular bandwidth is reserved for regulator growth, which comes with token based utilization, which will go later. And during the live migration, I think instead of providing CI max as the max for the usage for any particular customer, I think there is a high cap limit which is provided, which is the host provided limit. So this is the IHT which is provided. So during that particular time, like this is still available for instantaneous growth, but maybe for the during live migration, this part might be not available, and we will go back here. We will come back here in the next slides. So how does the live migration things happen? So first of all, every second, the fleet manager carries out 3-step procedures to determine if any live migrations are needed or not. So first of all, the first step is like we need to figure out which host need out migrations, which of the hosts are running hot right now, and how do we figure out? So for that one, like the fleet managers runs a heat aggregation per host. So basically it runs aggregation per host. It first of all, it checks if the summation of reserved RSUs. Reserved RSUs are the one which are currently reserved for my usage, which is the RI1 in this particular case. So we check if the summation of reserved ACUs for the host instance over the last few minutes exceeds one particular threshold defined. And this particular threshold is defined, I believe, like they haven't mentioned in the paper, but in my understanding, I assume this is defined at a fleet level. So they will define some parameter. And if and we call any host as hot if the current reserved ACU combined over all instances is basically exceeding this threshold, then we say that the host is currently hot. And another thing it try to does is if for all the hot instances which I have identified, if the usage crosses a threshold, if the usage is above this number, this threshold, then we basically freeze. We in that case, the fleet manager prescribe max ACUs for all their instances, which is this HIT, which we have seen in this picture here, where it's this HIT was prescribed by the fleet manager. But generally, like HIT is equal to CI max, which is provided by the customer. But during live migration phase, we do this. And this particular phase, like this has the effect of freezing all the resource allocation of the instances to their current value. And as soon as the heat has been dissipated via the live migration or drop in workload intensity, we basically remove these limits, and this HIT is again max to CI max of the customer, which customer max value which is provided. And this third step is happening only once if we know that usage is above this particular threshold, actually. So that's another thing. Once we have identified which host are the hot host for me, for which I need to migrate it, the second step is on that particular host, we need to figure out which are the instances which I need to migrate. And there are certain, I think here also they are using certain heuristics here, because there are multiple requirements or multiple criteria which they need to stick to. So for example, for the same memory size, an instance with a higher CPU or network usage may be a better candidate to be migrated. I think another decision we need to make sure is like we need to account for fairness also. We need to make sure how many times an instance is getting migrated. I think other things which can affect this is we need to also figure out what's the current memory image size and what is the dirting rate. Dirting rate as in like how many pages are getting changed during the migration phase itself, because we want to make sure the dirting rate is as low as possible so that all these live migration actions can be taken up at a much faster paces. So there are multiple decisions that we need to take, or there are multiple criteria which are there. So they take a heuristic based approach here. Uh, so first is the certain filters for migration eligibility are applied to reduce the number of instances to consider. So for example, if an instance was recently migrated, we skip those particular cases out. Second step they do is they do something called as preference ranking of filtered instances is created. And each preference score is a binary. It's a 0 or 1. And these preference scores are combined via weighted sum. So for example, like one score can capture if an instance was recently migrated or not. That's how they determine the preference ranking of all the filtered instances. The third step they are using two rankers to create a numeric score one per instance. So first ranker returns a score proportional to the reserved ACU for the instance. Basically, how I need this just to keep the number of migrations low. And the second ranker returns a linear combination of unused fraction of network RX in this one. Basically like network throughput, EBS throughput, and EBS IOPS capacities available to the instances. And we do a weighted sum from first ranker and second ranker to combine a single ranker thing. And finally, for this particular stage, an instance with the highest preference score is selected. And in case of some ties, then we go with the numeric score. And based on this approach, we have now an instance with us for which we need to do the migration to. Now, the third key decision which lies is where to migrate. I think we have already identified which is the host. The second step was I have identified which is the instance to migrate. Now, the third major question for us is where to migrate it. So the third step also is a heuristic based approach, which is a three-stage process. The first step is they apply the filters to ensure that the host is active. We would not exceed the heat threshold with the new instance coming there. It has the bandwidth to support the migration, and also the number of instances on the host is less than some threshold which is defined. Here also they do some preference ranking of host based on placement instance. So basically like we want like place the instance on the same cluster on separate host for fault tolerant reason. Also, we will prefer a host that don't have recent failures or were not involved in failure migrations. Then the third step is we compute two numeric scores and combine these via a product. So first is like a best fit like heuristic for bin packing and compute the score something like it's a ratio of heat on the host with the new instance over this is the migration factor which we have discussed earlier. So they try to see with the new host coming in what will be my new heat pattern looking like and ratio over this. And I think one more key pattern which they have highlighted, which was kind of new, uh, they do this to ensure that load is unevenly distributed among the host, such that some hosts have enough headroom for serving as live migration comes actually. And for this one, they are using this parameter. The second thing is they also use something called as 1 minus ratio of ASUs corresponding to the most utilized resource. So most utilized resource can be CPU, memory, or network, or something else. Depending upon that, we figure out what's the ACU for that. And then we take the ratio of this. And this has the effect of reducing the load imbalance across resources. Basically, like these are three key resources we are looking out for. So we need to reduce the load imbalance across these one. And just to keep a live example here. So for example, this is a diagram which is there in the research paper, in the paper itself. So and here all these vertical lines are showing one of the host, and this is the capacity which is available right now. And we can see this host S is currently running hot because I think this is already crossing our threshold, which is this one. It's already crossing our threshold. And we need to, first of all, we already have figured out this is the host on which we need to do the migration. The second part we need to figure out is which instance to do. So for example, this orange instances we have figured out for this, we need to do the migration to. Now for the host migration, like for migrating it, there are two instances available. Either we can do on host D or host D dash. And here we have chosen host D to do the migration. And I think this is just to make sure like there are to make sure we have some the load is unevenly distributed, even though like D dash has much more bandwidth available than this, but we are migrating here. So I think we are seeing that some hosts are left unrelated, unoccupied to facilitate large size migration later on. And whenever a new instance is coming up for that one, or when new instance of DB is coming up, for that they don't have any historical data. So in that case, system uses min ACU provided by the customer. And if any scaling up is required, that will go through the normal process of the Aurora serverless scaling up. It will go there and it can scale up quickly. So that's how they do the new system thing. Then the third aspect of fleet manager comes as fleet size adjustment. And fleet sizing is to make sure the fleet always have adequate host. And I think another goal is like additional host can be requested with enough lead time. And fleet manager employs a combination of like fleet level demand prediction and triggering additional procurement whenever a fleet utilization exceeds a predetermined threshold. I think, and currently they are also working on, I think, optimizing this one and going in depth here for fleet size adjustment. Another thing they need to keep in mind is whenever they are increasing the fleet size, as the fleet size increases, the computational and high frequency data gathering also increases with that. So they need to make sure like they should increase the fleet size to such an extent where these extra overheads are as low as possible. So till now we have seen like how does the fleet managers work and how does it figure out how to take care of live migrations and all. Another aspect of it is like how does the resource management within a host comes. So within a host, like we have something called as instance manager, which is a library that encapsulates Aurora serverless functionality within a instance. And it's a plugin Aurora instance manager, whereas rest of the functionality unrelated to resource management is there, which I think Aurora DB also provides. And we can see that like we have Aurora serverless instance manager here on the bottom. It is talking to operating system to figure out some of the resources needed. And we have something called instance specific agent also, which talks to the DB engine and figures out a couple of things which will go in upcoming slides. And we have a fleet management to which like our Aurora serverless management manager is talking to. It returns its resource usage statistics over certain time period. And fleet manager is some in case like the machine instance is hot or something, in that case it will come with a HIT recommendations also. So as we discussed, like host management manager also manager within a host also has a couple of responsibilities. The first responsibility is about the data collection. Instance manager relies on upon specific engine specific agent. And when I say engine specific agents, this can be like because Aurora is used mainly with MySQL and Postgres. So when engine specific agent might be Postgres specific agent or MySQL specific agent. So instance manager relies upon an engine specific agent for scaling up the buffer pool by a provider amount. It collects the engine's usage and estimates of its desired buffer pool size. And it employs its own internal algorithm for estimating these quantities and write them to a shared memory segment, which the agent can also read. Uh, so anything related to like buffer pool size and all those aspects is taken care by engine specific agent. And for all the other resources, like all instance manager gathers all other resource statistics except for buffer pool and all from the guest OS itself. It basically collects every second and collect in a in memory data report. And the frequency of collecting these metrics at per second basis is just to ensure responsiveness to the resource usage spike at a much finer time scale actually. Another big thing which this paper talks about is the virtualization solution. So as MySQL and Postgres, they are they are a DB engine which is there. So to provide them to run them in different VMs, virtualization solution is required. So each database instance is running in its own VM secured by hardware virtualization. And this basically provides strong protections between DBs, which are running on the host, and also strong protections among customers also against remote code execution, side channels, and other security vulnerabilities. So the team has tried Firecracker VMM solution, which provides secure, lightweight, and flexible virtualization. So this VM solution was able to provide them security needs as per their need, dynamic scaling of memory and CPU also, and per VM overhead as little as 5 MB. So the overhead was also very, very less. But as when they were testing out this solution, they faced high latency and CPU overhead of user space IO virtualization. And combined with the disaggregated storage design which they have, it basically like lead to performance and increased latencies for certain workloads with poor cache locality. So that's why they haven't chosen this solution as such. For virtualization, they built their own system, which was based on Nitro system, which provides Nitro low latency, and it basically like it was based on hardware IO virtualization, based on single root IO virtualization, and they are also taking care of CPU and memory provisioning. I think other thing which all the DB Aurora serverless instances are running on db.serverless and with the ability to grow up to size of 128 ACUs. And this new instance Nitro operates at 2 MB granularity to keep the page defaults overhead as low as possible. And they also added a couple of new features within the guest OS kernel to make it much more frugal in its memory usage. So one thing is memory offlining, which has the ability to dynamically release portion of its memory to the host. They also done some work on cold page identification. So a kernel process which monitors the page and identify which are the cold pages which are there. Another thing is like free page reporting, a daemon running within the guest looking for free pages. And if it finds any 2 MB free block, it reports to hypervisor. And another compaction related activity is currently going on. And whenever it tried to coalesce all the 4 KB free pages into 2 MB blocks. So based on this, like they were able to uh, keep the memory and offload the memory to a much better space. Yeah. Other thing which and there are two policies for the instance manager that it needs to take care about. One is the boundary management. Another thing is in place scaling. When I talk about boundary management, as we have shown in the picture, earlier. This HIT was provided by the fleet manager, this particular configuration. And RIT is provided by the host manager, or basically the instance manager running on the host. And this basically take care of in-place scaling actually for it. Yeah. So for in-place scaling, the goal is like we need to determine ideal scaling target. What should be the resource allocation for the engine? And currently a loop runs every 1 second and considers up to few minutes worth of per second historical usage data. Bulk of the data decision making concerned with resource specific deciders, each for estimating the instance needs for a particular resource type. And deciders are nothing but they convert its projection of its specific resource needs into a common currency of engine's buffer pool need. And these deciders, they take CPU, memory, network, bandwidth, IOPS, and different things and convert to a common currency. That's first thing they do. Another thing is they estimate the engine's buffer pool needs, uh, take the max buffer pool usage over the last few minutes at its projected buffer pool. And I think another thing for in placing is they respond to substantial change in recent CPU usage of the instance. They identify P50 CPU usage for last 30 seconds, P70 CPU usage for last 60 seconds. And once we have these two percentile numbers for last 30 and 60 seconds, we determine the corresponding memory sizes, which is mem 30 second and mem 60 second, based on the shape of an ACU. And if the mem 30 second is greater than current engine fixed memory, so basically like this condition basically says that our usage is increasing. Whatever I needed in the last minute, I need to use more. In that case, deciders target memory set to 30 mem 30 second. And if both 30 and 60 seconds are lower than current engine fixed memory, in that case, target engine fixed memory size is set to 60 seconds. And I think these two conditions basically like is to track, like is to just to say that potential scale down is considered more cautiously than a scale up. And apart, this example just shows you about the recent CPU usage. I think on a similar way, they have additional resource-based deciders for network and storage, also network received and transmitted, and storage bandwidth and storage IOPS. They have this one. And then the second step, once they have numbers or projection from all of these deciders, they combine them by taking their max. That's how they combine this. So after this step, like we have a single number which decides what should be my engine buffer pool memory size actually. Yeah. Another thing, and this was about in-place scaling. Based on this, like we decide like how in-place scaling should be there. Another thing is how do we define the boundary? How do we enforce the boundary? So there are two mechanisms by which instance managers control its instance CPU and memory allocation. One is the C group usage, which is a mechanism provided by in Linux operating system itself, where engine and instance manager processes are a part of one group, and resource allocations corresponding to a local ACU specified to this group. And for any CPU and memory on and off lining, basically VCP virtual CPUs and memory are added or can be removed from guest kernel to control resource group of the instance. And bringing additional CPUs can also help mitigate like noisy neighbor problem and help useful in ensuring good performance. For boundary management, another key thing is like how do you dynamically adjust the reserved ACUs? Reserved ACU is this factor which we have discussed earlier. Reserved ACUs is this factor which is available to us, which is available for instance growth for us. Yeah. So we have two main considerations to do here. One is like agile and efficient detection of growth trends. So for this one, like I think scaling band is the band which is like how much is my current usage and how much is my reserved ACU. So the difference between the two defines my scaling band. So we need to make sure we have appropriate scaling band for my growing resource needs also. And also we should also make sure that we are not over provisioning on that it's leading to wastage of resources. We need to decide, we need to make sure we are agile on both the fronts. So Instance Manager monitors the data memory footprint every second and maintains a history for last 1 minute or so and convert it into reserved ACU. It also looks at CPU usage, network throughput, and block device IO as well. And out of all these parameters, then it takes the maximum of this and determine like what should be the ACU there. For regulated growth as in like if when my usage is continuously increasing, and if I need to increase my reserved ACUs in a constant manner. So Instant Manager limits the scale up rate to give basically we are first of all we are limiting by how much we can scale up the usage and other resources. And we are doing only to give the fleet enough time so that like it can remediate the high heat on a host via live migrations. So we want to give that process also sufficient time. And this regulated growth is done in via a token bucket based regulator. Um, so as long as instance usage is below its reserved ACU, it enjoys nearly instantaneous scale up. So my resources can scale up as up to the reserved ACU. And beyond that, I think just going over how does the classical token bucket look like. So we have two parameter. One is what is my committed rate and what is my bucket size. And tokens arrive at a fixed rate of R into the bucket. And a resource allocation request is only satisfied if I have enough tokens in my bucket or not. And contents are adjusted in the bucket to reflect this discharge of tokens. I think we are using a similar kind of algorithm here, but instead of having a constant value for committed rate and bucket rate, these are defined as the increasing functions of current local max ACUs. So for R also they are defining R of a function of C, basically R is a function of C. So they also wanted to make sure that when we are at a very high intensities, so the workload tends to require more higher rate of growth at those particular times. So that's why this increasing function is used, so that like we can give higher rate as my if the workload requires that higher intensities. Also, like it limits the scale down rate also and allows enough time for low activity elapse before the scale down starts actually. These are some of the customer specific observations which they have given. So for example, in the first case, like there 33K instances were there, 33,972 instances were there, and they exhibited these many scale up events or basically scale up or down events actually. And out of these events, only these events were there where one or more live migrations were needed. And average number of live migrations whenever these were happening was around 1.68. And out of these scale up events, only 160, 198 were such that like it uh, where when the host reached this particular threshold, that is like instance reserved ACUs were temporarily held. So only these 198 times over a period of 17 days when my resources were temporarily held. And on a similar case, like they have given this. So on a high level, like we can see, first of all, the average number of live migrations or scale up events for which the live migration needed is very low. That's one thing. And also for live migrations also, whenever they are holding up the resources, that count is also very low actually. I think, yeah, that's all I have.